so excited for the quiz and exam and projects, right? Or you got excited about the Thanksgiving? All right. Well, just bear with me for one more hour for the rest of the semester, okay? Then I'm done, okay? All right. So what we're going to do is we started of a modification factor. If you still remember, it has been a while since we had a lecture, right? So we discussed the first three parameters, Ka, Kb, and Kc. Today we're going to discuss the rest of the three parameters, and then followed with three questions. So we'll be done. Okay. All right. So let's look at Kd. Kd is the temperature factor. Oh, by the way, so just want to catch up. Did we mention anything about Kc? No? Just Kb? Okay.
Kc load modification.
Sure. Okay, so Kc is called a loading modification factor, or in short, is loading factor. So Kc is really easy. Mainly, there's three coefficients you can choose from based on the type of loading the shaft is undergoing. Okay? So if we have bending, then Kc is just equal to 1. Or if you have axial loading, then Kc is equal to 0.85. And if you have torsion, Kc is just equal to 0.59. All right. Now, chances are you're going to see combined loadings, right? In a shaft, especially, let's see, not exactly. The project 2 we did is mainly just bending, right? There's no torsion going on. So if you have combined loading, you have all these three loadings together. What do? What is your Kc? Huh? You know, it's multiply of all these three together, right? Because you see all the parameters, they multiply together, right? So if you have combined loadings, three different loadings, then it's just equal to multiply of each one, all right? That is your Kc when you have combined loadings. Yeah. So if you have all three loadings, you multiply 3 together. If you only have 2 of the 3, you multiply 2 together, all right? That's what you do, okay? All right, so relatively speaking, easy. So the next one is temperature factor. Kd. All right. So temperature factor is trying to compensate for the material property as a function of temperature. So if we have a plot like this, x-axis temperature, y-axis is tensile strength, okay? So for most of metal, it looks like this. So we know at extremely low temperature, of course, material become brittle, right? So it's easy to break. So therefore, room temperature is around here. At high temperature, of course, we know everything becomes soft. I shouldn't say everything, but most of metals, right? Steel. That's why you have to heat it up to do all the forging or the hot roll, stuff like that, right? So therefore, the mechanical property of the materials we use is a function of temperature. So the temperature modification factor is introduced to compensate for the temperature influence, okay? So this is also relatively speaking easy because they did a bunch of testing for most of the structural steel. The property as a function of temperature is quantified. So this table here gives you different temperatures: 20, 100, 200, 300, 400, and 500. These are typical temperatures most of the shaft will be seen, okay? Now, RT stands for room temperature. T, this ST means the tensile strength. So basically, this ratio is the tensile strength over the tensile strength at room temperature. Okay, so of course room temperature we always take 20 degrees C, right? So it's 1.0 at a room temperature. So when it's 100, it actually increase. 200, it also increase, but after that, it start to decrease. Okay, so this KD is just equal to ST over SRT. So RT stands for room temperature again, all right? So the reason why it'll increase and decrease is because of this. You look at this plot, right? Room temperature is over here. Most of the metal, especially stainless steel, the property will increase first and then decrease, okay? So that's why. Anyways, I think we should be good. I'll cancel that. Boring. Okay, so the next one is my reliability modification factor. KE. All right. So it's also very easy, just a table. Reliability, when usually we use percentage and a KE. So here on the first column is your reliability. This is also based on statistics, all right? For example, if you make 100 shafts and you want to make sure 50% of them will satisfy your requirement, that's called 50% of reliability, all right? The other 50 can fail, okay? Now, when you have 50%, KE is just 1, and then when you increase of reliability, this KE will decrease, which I will tell you why it's going to decrease. Okay, so reliability is very similar as design safety factors, right? So let's see here. If I want to have a 99.9% of reliability, so basically maybe the component is very critical, okay? So I want to make no mistake. So I set reliability to 99.9%. So therefore, your KE is a relatively speaking small number. Now, what does modification factor do? It gives you this, right? So if your modification factor is less than 1, it brings the endurance limit down. So in other words, when you have 99.9% of reliability, the loading you can apply is lower. Makes sense, right? Because the higher load you apply, the higher chance it's going to fail. Makes sense, right? Okay. All right, so that's pretty much it. And then KF is just a miscellaneous factor, so we don't have to discuss with it. Okay, so next, we're going to look at 3 examples. Before I go to the example, there's some fundamental concept I want to introduce. Very easy, very quick, all right? For fatigue strength. So all we're doing in these months, in the past 2 or 3 weeks, is we're trying to look into dynamic failure, fatigue, right? So when we have fatigue, of course, we're looking at the strength, the maximum load you can apply, or the maximum number of cycles of load the material can undergo before failure, right? Okay, so the fundamental equation to quantify the fatigue strength is this. So this SF prime N equals to sigma F prime 2N times B. Looks like a statistics equation, huh? Okay, so this SF prime is called specimen fatigue strength. Specimen fatigue strength. Okay, so let's see what's the other one. The sigma F prime is called fatigue strength coefficient. Or sometimes people call it true strength. Okay. All right. Now n, of course, is number of cycles or number of loading cycles. Okay. All right. So, for example, if we say at 10 to the 3, which is 1,000 cycles, this SF prime 1,000 equal to sigma F prime 2 times 10 to the 3 B. So, you know, what we do is, what?
Thank you.
What?
Thank you. Is it 18 divided by D or?
Which one?
Add the cycles after the cycle to the cycles.
Add 10 to the 3 cycles. So add 1,000 cycles. What about it? What's wrong with that?
I thought it said A divided by D cubed.
A divided by D cubed? Where? You talking about this one?
18.
Here?
They got it. So
Yeah. Above.
What about it? SF prime of 1,000.
Oh,
divide by 0, 0, 0? Anyways, alright, I'll just keep on going. Okay, so that tells you, see here, SFN means what? See, the subscript tells you its number of cycles, right? So when I have a 1,000 cycles, so therefore this is SF prime at 1,000. Okay, so equal to sigma F prime times 10 to the 2 times 10 to the 3 to the power of B. All right. So basically, at all this is you set n equal to 1,000. Okay. So most of the time, what we can do is we can also say this equal to F times SUT. Why? Because the sigma F prime is nothing but just the true stress. So when we have a true stress, we know the maximum stress every material can take is called a strength, right? So it's SUT over here. Now, whatever this B over here is just a coefficient. So we can just say whatever inside its parentheses to the power B is F. Okay, so that's a coefficient. So in other words, F equal to sigma F prime divided by SUT 2 times 10 to the 3 to the power of B. Okay, now so typically sigma F prime equal to SUT plus 50 KSI, or sigma F equal to SUT plus 345 megapascal if you use metric. So basically the true stress it's seeing is related to ultimate tensile strength of the material you use. Alright? Okay, again, all these analysis we're doing is related to shaft. Okay, because shaft is the most fundamental element that sees lots of cyclic loadings. Okay? Alright, so here we couple this knowledge with endurance limit. So endurance limit we know is SE prime, right? So SE prime equals to sigma F prime to NE to the power of B. Okay, so this SC prime divided by sigma F prime is nothing just equal to 2 times NE times B. Now this E over here stands for endurance. And therefore you can do a little modification. Now NE is endurance limit, so basically most of the time E is just equal to 10 to the 6, right? So when any of the material in engineering can undergo 1 million times of a cycle, we consider that's the endurance, okay? So typically NE is just equal to 1 million, okay? All right, so this parameter, we never see it, right? So B, okay? So what is B? You can do some calculation. Okay, so you do log on both sides, and then you move things around, and then that's it, right? So the reason why we have to estimate B is because, see this equation here. The fatigue strength can be estimated by this equation, right? So this B is a coefficient that we don't know yet. So we have to estimate B first in order to get fatigue strength, right? So in other words, this is the equation you need to use to estimate B, okay? That's a coefficient. Now, also, we have another parameter F, which is another modification factor that is directly related to ultimate tensile strength. So usually F will decrease with the increase of your ultimate strength. So in other words, you know, if the ultimate strength is high, means that material is more brittle, right? So therefore, the F is lower. Anyway, most of the time, you can find this parameter F in the book. So therefore, if I ever ask you any questions, I'm going to give you the F, so you don't have to find the F by yourself, right? Okay, so, and also, in some cases, you see this SUT starts at 70. So if the ultimate tensile strength is less than 70, so F is just equal to 0.9, okay? All right. Okay, so here we have a very powerful and useful equation which we need to use for estimation. SF equal to A times N to the power of V. So this SF over here is called endurance strength. And this N, of course, is number of cycles to failure. Okay, so in terms of, in other words, how many times a cycle it'll undergo before failure happens, all right? And A is another coefficient which equal to F times SUT squared divided by SE. And B is another coefficient which is different from the B we learned before. Minus 1/3 log 10 F times SUT divided by SE. All right, so SE, we know what's that, right? SE is endurance limit, okay? And A is defined by this, and then B is defined by this. So we can calculate A and B easily once all the conditions are given. Okay, so why we need to have SF? SF tells you the endurance strength. So it can quantify the number of cycles of the material can undergo before failure. In the same time, if I give you certain number of cycles we need to undergo, then we can calculate the endurance strength. So these two parameters, they are coupled with each other. A and B are just constants, right? If I give you SF, you can calculate N. Or if I give you N, you can calculate SF. Make sense? All right. So next, let's look at the examples. Before I go there, just tell you how to calculate N. So N equal to SF divided by A to the power of B, 1 over B, right? So in other words, you can calculate the N from there as well.
Can you go back up?
There you go. Oh, this is your question? Okay. Are we all good? Okay, how about now? What's so funny? Huh? Okay, all right. You guys get us super excited, huh? Today's the last lecture, right? All right. Okay, so F equal to 0.86. And there's a steel with a tensile strength equal to 90 KSI. So find A, endurance limit, B, endurance strength of a rotating beam with 10 to the 4th cycle So basically, there's a beam made out of this material, but has to undergo 10 to the 4th, 10,000 cycles of loading before failure, okay? All right, so C, by the way, this is a very important example. I guarantee you will see it in an exam, all right? Does it make you excited? So the expected life, which is number of cycles, of the same beam with SF equal to 55. Okay. All right. Okay, are we all good? Okay, so first one, endurance limit. So now, if you open your notes, probably 2 weeks ago, when we first introduced the endurance limit, we have a quick estimation of endurance limit for most of the steel. For steel, the endurance limit, first over, let's say, so SE is my endurance limit equal to either half of its static strength or equal to 100 KSI or 700 megapascal. It's when your SUT is less than 200 KSI, or when you have SUT that's bigger than 200 KSI, or if you use metric, 1400 megapascal. Okay, so that's a quick estimation of endurance limit. Remember, before any modification factor comes to play, right? Okay, now here's the example we have. So the condition gave us is, let's go back. So SUT is 90 KSI, right? All right, so we come here, 90 KSI, of course, it falls into this catalog, right? It's less than 200. All right, so we can have a quick estimation of endurance limit. So should equal to half of the SUT, which equal to 90 KSI. So the answer is 45 KSI. That's easy, right? That's it. So now a quick review. What is endurance limit? What does it do? It tells us when the dynamic loading has a magnitude less than 45, it's going to have infinity life. Remember the plot we had? Remember we have a plot like this, right? This is number of cycles. This is endurance limit. This thing over here, right? Remember that? Okay. It's alright. I don't blame you if you don't remember because I can't remember either. So, anyways, so that tells you this is a dynamic loading limit you can apply. Okay? Okay. That's question A. Question B. Oh. Question B is asking us for endurance of strength, where you have a number of cycle equal to 10 to the 4, right? So remember that that equation we have is nothing but just equal to this, right? So question B is asking for endurance strength, which is asking for SF. It gave us N equal to 10 to the 4. All I need to do is find out A, find out a B. Makes sense, right? Okay. All right, so let's see how we find out A. A is equal to F times SUT divided by SE. Here you have square over here, so plug it in, all the parameters. F is given 0.86 modification factor. SUT is given as well, 90, right? Square. And SC will just calculate it, endurance limit, 45. Okay, so that is 133.1. Okay, we're done. And then next, let's look at B, equal to minus 1/3 log 10 F times SUT divided by SC. So also plug in all the numbers. Log 10. Again, F is 0.86 86. SUT is 90. And SE is 45. So that should be easy as well as long as you calculate out. Okay, so that gives us negative 0.0785. Okay, so what do we do next? Plug it in, right? That's the answer. Okay, so SF equal to A and B. Okay, A is 133.1. N, what's N? 10 to the 4, right? So B is negative 785. All right, so calculate everything out, equals to 64.6 KSI. All right, let's have a discussion. Okay, so this is my number. What's SE here for this case? Endurance limit. What is it? 45, right? We just calculated it. What's SUT here? 90, right? All right. So this is when we have 10 to the 4th cycles of loading, right? This, simply speaking, infinity, right? Now, recall that plot. This is your strength, starting at SUT and all the way go down to SE. So this is number of cycles, so which is N, right? So it goes down further, and it stays stable. Okay, so 45 is my value here, equal to 45. Now, 10 to the 4, probably, remember what I said over here, usually if it's more than 1 million, that's infinity, right? So 10 to the 4 probably fit somewhere here, right? Now, if you go up, try to find this number over here, it should be what? Higher than 45, right? So this number over here, higher than 45. Makes sense, right? That's easy, right? Imagine when you try to bend a copper wire, the higher the number of cycles you apply the load, the higher chance it's going to break, right? So at a 10 to the 4 cycles of load, of course, the endurance strength is going to be higher than endurance limit. In other words, these two values actually they are the same measurement. In other words, endurance strength means number of cycles of loading, what's maximum load you can apply, right? And an endurance limit means if it has infinite life. But most of the time, like I said, if it's more than 1 million, then that we consider that as an infinite life, right? So these are all measure of maximum load you can apply under that number of cycles of loading. Make sense? So if I have dynamic loading, if it's symmetric, time, here is load. This number here, when higher to lower, is called revolve stress, and most of the time we consider that the same as the SF, which is fatigue strength here, right? So in other words, if this N is smaller, of course this SF will be higher, right? Okay, so don't worry if it's not too clear. Let's look at question C. It'll be further strength knowledge, right? So C means SF is equal to 55 KSI, and we're looking for this N, right? So the equation we need to use is N equal to SF divided by A to the power of 1 over B. Okay, A and B will calculate it. SF is given, we can calculate N, right? 55, 133.1 to the power of 1 over 785. Why you guys are so excited today?
0, it was 0.0785.
Yes. Okay, so you plug it in, that equals to 77500 cycles. So 77,000 cycles. Okay, let's have another discussion. So question B, it gives us when n equal to 10 to the 4, SF equal to 64.6. Now this is what B give us. C, it give us when SF is equal to 55. Then we calculate n equals to 77, or in other words 7.75 times 10 to the 4th. Now question B and C, do the answers make sense? If you look at them. So which one has higher number of cycles? B or C? What? You Diego, right?
Sí. Huh? Andrés.
Who says B?
Andrés.
Of course it's C, right? Okay, so B has higher number of cycles. So at a higher number of cycles, you would imagine the endurance limit or endurance strength will be what? Lower, right? Of course. So in order to achieve 7 times 7.4, so 7.75 times 10 to the 4, you have to have a lower loading, right? Because the higher loading you apply, the less cycles it'll endure, right? So that's why it's called the endurance limit or endurance strength. Yes?
If you scroll up a little to the tape, to the graph that you have at SUT,
Mm-hmm.
ultimate tensile, right? Does it fracture right there, or can you apply? Will it last like one cycle?
Yeah, that's one cycle, right? Here is 10 to the 0.
So it doesn't fracture there. It actually lasts for one time of use.
Yep.
Theoretically. Right?
Yep. All right. Don't worry, I still remember you said B is higher than C. Yeah. Okay. So in other words, when you have higher loading, higher dynamic loading, 64.6, of course, the number of cycle will be less, right? Okay, so that totally makes sense. So in other words, SF and N, they're inversely proportional to each other. Higher N give you less SF, higher F give you less N. Make sense? All right. It's all from this plot. Remember that, okay? This is number of cycles, and this you can consider as SF, okay? It all goes down, okay? All right, so very important example. So let's look at one more. This time let's do something interesting. Let's couple with the stuff we learned. This is one of my favorite examples, so I guess probably we'll do that in the quiz or exam. All right. We'll keep the best to the last. All right. This is the last example I'm going to give you for the semester. All right. You gotta cherish the moment. Okay, so if we have a hot rolled steel ball with SUT at room temperature 70 Fahrenheit, 20 degrees C, equal to 50 KSI. Is machined to a diameter of 1 inch, right? Okay, so that's the machining condition or surface finish condition. Now, it is designed to be placed in dynamic loading of 70,000 cycles. All right, so n equal to 70,000, right? So number of cycles to failure is 70,000. With operation temperature of 550 Fahrenheit. Maybe it's in an engine, all right? So therefore the temperature is higher than room temperature, right? Okay, so using a reliability of 99%, what kind of question do you guys have? Have any questions? 99%. Estimate the endurance limit and fatigue strength. All right, I really love this example. Why? Because it combines the knowledge we learned in dynamic failure and in the same time combines the knowledge of the endurance strength and the endurance limit, right? So all the things we learn about dynamic failure is concentrated in this example, all right? So here, I'll give you a couple conditions. F equal to 0.9 and ST over SRT at a 550 Fahrenheit equals to 0.979. Okay, so let's see here. Let's look back a little. So the other two conditions, right? Now, first of all, it is a steel ball, it's hot rolled, and then they machined, right? Then what's going to happen is that it has diameter of 1 inch, and it has to undergo 70,000 cycles to fail, right? To failure. The operation temperature is also high. So when you have all these conditions, what do you think to do first? Right, you have modification factors to consider, right? Because you have higher temperature, you have different surface finish, and you also have reliability, right? Also, it's asking us for two things: endurance limit and fatigue strength. So it's asking for SE and SF at 70,000, right? These are two things it's asking. All right. Okay, so first of all, we know when you have modification factors, this CD here. this is what you can do, right? When you have modification factors. So this is our first step. In order to do that, we need to know what's the modification factors, what is the endurance limit before modification, right? Okay, so here SUT equal to 70 KSI, which is less than 200 KSI. So we automatically know this SE prime equal to half of the static tensile strength, which is equal to 35. Oh, sorry. I say 50, right?
Yes.
I take it back. 70 is the other one. 0.5 times 50. So that is 25 KSI. Alright, so that is my endurance limit before any modification, right? So that's my SC prime. I have it. So next, I need to find out Ka, Kb, Kc, Kd, Ke, and Kf. Okay. All right. First of all, Ka is my surface finish. Ka, we have this A SUT to the power of B. That's what we do, right? Okay. Surface finish. If you remember that table, there's two conditions here. First one, it's hot rolled. Second, it's machined. So if you open that table, we have forged, grind, hot rolled, and machined. So when you have two surface finish conditions, which one do you choose? This is actually, it's a little different. You choose the last one because first of all, the steel bar is hot rolled and it is machined. So therefore, the last surface condition is machined. So therefore, you choose machined. Make sense? The loading is simultaneously existing there, so you have to multiply. But the surface finish, you only look at the last surface finish the bar did. Make sense? All right, so just machined. So once you do that, then we find out it's a machined. A is 2.7, B is negative 265. All right, they're roughly equal to 963. All right, so that's my Ka right there. Okay. All right, so the next one is my Kb, and it is also said we have a reversal axial loading, right? Oh, sorry, I missed the one condition here. It's dynamic axial loading, all right? So all the loading are in axial. There's no bending or other things, right? So axial loading. So Kb is equal to 1, and Kc when it's axial loading is 0.85. Okay, and this thing over here, Ke reliability, so that's equal to 0.814. Kd is my temperature. That is just equal to 0.979. Yes?
Why did you pick 1 KB?
Kb is diameter, right? So therefore, once you have 1 inch diameter, if you look back, if I remember right, and then that's just the 1. Okay? All right. So Kf is MECH. So MECH means a bunch of other things. So it didn't mention, therefore we just choose 1. Okay? So in other words, Kf, unless I specify, otherwise you just choose 1. Okay? All right. And next, once we have all these what you do is you plug in all these things. X is 3.85 times 1, 0.979 times 0.814 reliability, and the last one is my SE. I can't write over there, right? So times 25. Okay, so the answer should be really close to 16 KSI, which makes sense. Why? Because the endurance limit is 25. With all the modification, it brings it down, right? It always brings it down. The only parameter might go up is temperature, but here the temperature is 0.979, right? Because all the parameters are equal or less than 1. Okay, so the number is less than 25, makes sense. All right, so half of the problem is done because we are asking for these two things, right? So SE is right here. The next is we need to look for SF. Again, SF, let's see what we have, right? That's the equation we have. N equal to 70,000. All I need to do is find out A, find out B, and that's it, right? Okay, A equal to F SUT square divided by SE equals to 0.9 times 50 divided by 16.3. That's what we calculated just now. Oh, make sure when you calculate A and B, this SE over here is modified endurance limit. It's modified, okay? Make sure you remember that. So this number here is modified. It's not the SE prime, okay, which is theoretical value, okay? All right, so that's my answer. B, doing the same thing. SUT, SE. Again, plugging all your numbers. Minus 0.9 times 50 divided by 16.3. That is my answer, which is negative 0.1441. Okay, so one last step. SF equal to 119.3 times 70,000 to the power of negative 0.1441. Okay, so that gives us 23.9 KSI. All right, so this is my endurance limit. Sorry, endurance and strength at 70,000. So 70,000, you would imagine that's going to be higher than the modified endurance limit, which is 16.3. Right? That makes sense. Because usually for SE, it has to be more than 1 milling, and 70,000 is way less than 1 milling. So therefore, the loading is higher, right? Okay, so let's do one more thing, all right? One more thing. So, like we said, equals to A and B. That's what we did, right? Okay, now, if this N here is more than 1 milling, you would imagine this SF will be really close to the endurance limit, right? We'll give it a try, okay? So who has a calculator? I need some help here. So what if we have 10 to the 6 times B? And here, A is 119.3, 10 to the 6. B is negative 0.1441. What is this number equal to? Who has a TI calculator? Can you help me to calculate this? Extra point? Nah, just kidding. Now you guys are doing it. Huh? 16.2? Huh? 29? Right? What is our SE?
16.3.
Oh, what do you think?
It's pretty close.
Right. It's because endurance limit is based on number of cycles equal or more than 1 million. If you plug in more than 10 to the 6, maybe 10 to the 8, it'll be even closer, it'll be even a little lower. But endurance limit is... Alright, I have another test to do. Alright, anyways. So therefore, now we know endurance limit means n equal to 10 to the 6, right? So endurance limit and the endurance strength, they are related, just that the n is different, right? It's cool, huh? All right. Okay, so that's the end of my lecture, and the rest of the class will be all on you guys, all right? Okay. All right. Thank you, guys. Oh, by the way, I have your project report here. Feel free to. Group number 2. Group number 2. Group number 7. 7. Number 3. Group 3. Group 4. Group 5. Oh, thank you. Group 6. And group 1 right here. Group 12. Group 12. Here. Group 11. Right here. 9. Group number 9. Group 9. Group 8. Group 8. Group 8? Group 8. Yep. Nice, someone got it already. All right.